Okay, sorry for the pause. Um, so this one, what's different from this one? Well, you notice it's got only one voltage source, but this voltage source split. It's shared between two 2 points here and here, and these 2 points, they have their own resistance. And you may wonder when you see something like this, is how you calculated when there is one voltage source coming in. Alright, so let's get started with the red pen. No current first of all. Second of all, this pin will be the V1 and this pin will be V2. Next up is this point here that you wonder. Well, think about logically. So there's no resistance in here, so then this point here will be equal to this point here. Alright, so this one will still be 2 volts. But also there's no resistor at this point and there's no resistance at this point. So we can say that there will be 2 volts at this point and there will be 2 volts at this point. So you can ignore this part here and just focus on this side, where there is 2 volts coming in this direction to here and there are 2 volts coming in this direction to here. It's a bit strange with op amplifiers, isn't it? Usually when you see a circuit, let me get a page so I can show you. And that's why I find like op amplifiers being different and difficult for some people, is that when you see a circuit like this, you know, you see here one of them, you see like one like this, the capacitor, let's say, and then you see with an inductor here, something like this, plus minus, and this one it's V in, and this one is nothing, and then you see them connected, let's say like this. In a normal circuit, you'll say, I do not want it like this. It's too spread out. I want them to be closed and logical. And then when you close them, you'll get something like this. This one stays the same. There's the junction with the inductor on this side and the resistor on this side, and all of them are connected to a common ground here. And you may say, like, I mean, sometimes it's objective. You may say that this circuit is far easier to calculate than a circuit that's in this format. With op amplifiers, it's kind of like the compressed opposite, as we saw in a few examples. Like in this one here, for example, this one, they are coupled together, but inside an op amplifier, you don't want them to be together. You want them to be spread out. And we'll have like multiple types of examples where they are connected together, and that makes it very hard to calculate and to understand what's happening inside of it. But when you spread them out, then it becomes a lot easier. So also I'm talking because this is another very short example, because as you already noticed, this is a simple inverting because it's on the minus pin, but it's got a voltage divider here. So it's an inverting with a voltage divider amplifier. We can call it like that. Alright, wait, this is the red pen, I need the black one. So then we can say that V1 is equal with V2. V1, this V1 will be, it's a current divider, they are not going through it, so it's a voltage divider through I. So we can say V1 is equal with 2, the voltage, multiplied by 4K over 4K plus 3K. Voltage divider rule. Alright. Now, after I did the calculation for this, so that will be 8K over 7K, and that will simply be equal with 1.143. And also V2 is equal with 1.143 because V1 is equal with V2. Alright, then next step will be to calculate this inverting. So it will simply be 2 volts minus V2 divided by 2K. So that will be 2 volts minus V2 divided by 2K equal with, because of Kirchhoff's, because it's current I going through it and the same current I is coming out here, V2 minus V out divided by 5K. So that'll be V2 minus V out divided by 5K. Alright, and we just replace V2 with the value of 1.143. So 2V minus 1.143 divided by 2K is equal with 1.143 minus V out divided by 5K. Therefore, 4.285 times 10 to the minus 4 will be equal with 1.143 minus V out over 5K. Therefore, with the 5K multiplied by this value here, that will be 2.143 equal with 1.143 minus V out. Therefore, minus V out will be equal with 1. Oh, it is actually 1. That's surprising. It will be 1. Therefore, V out is equal to minus 1. And I guess if you want, you can calculate the gain. So like V out over V in will simply be equal with 1 minus 1, so it's minus 1 over 2. Therefore, gain is 0.5. Yep. Alright. No, actually it's a minus 0.5 because it's a negative. I guess you can write it like this. So this is how we solve this problem here. Again, if you think an op-amplifier is too complicated, it's got too many connections together, bundled together, just spread them out and to make it a lot simpler. For example, like this one here, you know, from a complicated one that looks like it's got a common connection here with the 2 volts, it switched to a very simple one. Alright, I'll see you in the next exercise. Here it's another very simple one. But this one has got the current source, because we haven't done any of them with the current source. And also, it won't be asking us to find the voltage output, it will ask us to find the current. And this problem, it's extremely simple with a current source. And why is that? Well, if you think about it, the current I will simply go through here. You know, it says the same, it will still be 4 volts. And it will also go through here because there's no current going through here or here. This is basically in series. So it's the same current I. Let's put I in. The same current I in will go through the 4K and it will end up here, I in, coming inside this node. Alright, and also it's I guess it's another current, so that splits at this node. This is connected to the ground, so current will tend to go to the ground. So then there's a current coming in this direction, and let's call it I out. Now we know that I in is equal to 4 milliamps, so let's write it down. So I'm sorry, that's the blue one. So I in, we know it's equal with 4 milliamps because that's simply the source. You know, the source keeps going through, it's connected in series, and the only point that it changes is when it reaches this node here. Alright, now I, this current here, is the unknown, we don't know it. And we also don't know I out either, is the unknown. So we need to find one of them. We ideally want to find this I here, but it's not really possible because it's got only one resistance, but we don't really know the current of it. So what we need to find out is that I out in here. Now, there are two ways to do it. And I'll show you both of them because this is pretty fast. The way that I prefer to do it, and I think is the easiest, is with a current divider. Alright, so what do I mean by that? Well, we know that this current here, I in, is coming in this direction, and we also know there are two different currents in here. Alright, now wait, Wait a second. Oh no, we can't apply current divider, can we? Because, so two currents are coming in, that's fine, but it's I out coming out on that direction. Alright, so then this will be 4 milliamps, and we multiply by the 4k, and then, but this one will mean it will become a negative one, negative current. Let's try both ways and see if it works. I don't, actually, if I think about it, I don't think the current divider will work here. So let's say I, it's equal with this current here. Yeah, it won't work because they have different directions. Yeah, we need to use I out for it, but we don't know the voltage here yet, and that's the problem. Sorry about that. We can't apply current divider rule because the current divides at, it doesn't really at this point. So if we knew I out, we could have applied it in reverse to find I, but we don't know I out, so we can't really apply it in reverse. Okay, that makes sense. Sorry, I thought we can apply the current divider rule, but no, because the current goes in different directions. Alright, let me get the page again that we used. Alright, but if you don't remember the current divider rule, which I'm surprised if you don't, is that basically, and let's put the resistance here just for the sake of it. Basically, it says that the total current here, I, is spread in two parts, in I1 and I2, and it comes out as I, and that's what the rule basically says. It basically helps you by doing, let's call this one R1 and R2, by basically doing I1. Let's say we want to find out I1, then you have to multiply the I, the total current, by the resistance 2, the opposite resistance, and then you do R2 plus R1, and you do the same formula for I2 as well, but instead you replace it with the opposite resistance, which will be R1 in here, and then you find I. And I guess that won't work for us because what we got here, it's again, we got the same thing, but the problem is that the I input, I in, is coming in this way. The problem is that I out, no, I, the one that the unknown, it's also coming in this way, and the only one coming out from this node here will be I out. So then this one here will be something like this, will be I out probably. So yeah, we can't really apply because the directions don't match with each other. They are not really a current divider rule. They are not spreading from one current into currents. Instead, it's like combining two currents in one current, so we can't really apply it. Sorry about that. But at least the more we know. I didn't realize that I can't always apply the current divider rule. You don't usually get something like this, you know. Anyway, don't worry, I have two methods for it. The second method is to find V out. Alright, so how do we find V out? Well, V out is equally here at the point here, and these currents when multiplied should all give you the same voltage output. So what do we do? Well, we know there are 0 volts at this point here, 0 volts, and because it's a ground here and it's only current going through, and it's 4k ohms in here and a V out in here. So what we can do is to say that so I in, this current here, we again use the made up Kirchhoff's law. I in, it's equal with the I in here, which that will be 0 minus V out over 4k. And now we replace them, therefore I in we know is 4 milliamps, equal with minus V out over 4k. And we do 4k multiplied by 4 milliamps, so therefore 16 will be equal with minus V out, and therefore V out will be equal with minus 16. Alright, it makes sense it's a minus because this is an inverting amplifier after all. Okay, now let's write from this node here. So I out will be equal with the current I, the unknown, plus I in. Alright, now we know the voltage V out, so we can determine now I out, because V out is minus 16. So then I out will be equal with minus 16 minus 0 over 4k, and that will be equal with minus 4 milliamps. All right, so that'll be I out. So then minus 4 milliamps is equal with I plus, and in bracket I in, we know it's 4 milliamps. Okay, no, okay, this is something that's wrong here. So the current is coming from this point to this point, which is V out, and this one is 0. It's kind of ironic because I said this is a simple one. Alright, so V out minus 0, but this one is minus 16, and that's the big problem here. The problem is that, you know, it's a negative value, so if you get here like if you get a positive 4 milliamps from this point, then this will basically just be equal to 0, and that's the whole so this will basically be equal to 0, you know, and that's the whole problem of it, because it will imply that I it's equal to 0. But maybe this is correct actually. Okay, so let's not solve it yet, let's instead input I as well. So then I will be minus 16 over 2k. Okay, so then minus 4 milliamps, it's equal with minus 16 over 2k plus 4 milliamps. All right, so then we can move it to the other side, so that will be equal to 0. So that will be 0 equal with minus 16 over 2k. So I guess therefore I will simply be equal with, so let's do 16 over 2k. It should give us minus 8 milliamps, and it probably does. 16 over 2 times 3. Yeah, it does give us 8 milliamps. Alright, minus 8 milliamps. Okay, and that's the answer. Alright, I guess I confused myself with it, because I guess I was expecting to get a different answer. This is so strange, isn't it? Because like if I left it as an I and I did 4 milliamps, but it's a positive 4 milliamps. Oh my god, now I get it. Sorry about that. Okay. That's it. I'm so dumb. I thought this one will come as a negative and you get rid of this one. No, and therefore I will be equal with minus 4 milliamps. Minus 4 milliamps. So therefore I it's equal with minus 8 milliamps. Okay, sorry about that. I don't know, I confused myself. I had the impression if I move this onto the other side, that will like get rid of both of them, they'll be equal with both of them, but no, actually no, it's still minus 8 milliamps. Well, there you go. Like, let's say that you have now two ways to like calculate it. You can just either do 0 minus VO by applying Kirchhoff's law over 2k, and because you know VO it's minus 16 volts, you can just apply that one and get the current. Or if not, you can do this on I out is equal to I plus I in, and that way you find out the cell. So I guess you have two methods in here. So sorry about that. And I was wondering, like, I don't know, sometimes like, I don't know, sometimes I guess I just don't pay attention, and it's something that I should fix. Hopefully, like this lectures, not really lectures, me trying to explain to you how to solve problems really showed me that sometimes I just don't pay enough attention to one calculation or one symbol, and it mixes up everything and like messes up everything. Hopefully it doesn't happen when I really need it, when I'm doing an exam. But anyway, thanks for watching this problem and being patient about it. So yeah, I guess we learned a little bit about like current division here, where you can't apply it, and I guess also we learned that we need to pay attention to the signs. Anyway, thanks for watching, and I'll see you on the next exercise. Alright, welcome again. So this next exercise, and again it looks very complicated, but it's actually really simple. Now, what do I mean by it's really simple? Well, let's start with the beginning. So, okay, let me think how to articulate. So we start with these 2 points. There's no current, there's V2 here is at the negative and V1 is at the positive, you know, the usual stuff. But this time we need to simplify a circuit. So we see that the negative side of the voltage source is connected to the negative side of VO in here, and also this side is connected to both of them. So we can say that all 3 things are simply connected to ground. Okay, now from a few examples ago, there's another node, and this node would be 8 volts, meaning that this node here and this node here, they will be with 8 volts as well, because they are in parallel, so they are the same. Alright, okay, then we can get rid of this diamond shape, and we can make this more into a rectangular shape, because these 2 basically are in series, so I can just draw them in a line like this. Okay, so let's get started by redrawing it, because this example is more about how you can vision it and how you can redraw it. Alright, so let's start with the amplifier. We'll put it around here so we have enough space. There is a match calculation. This example, again, it's only to like simplify a circuit. Okay, then this is VO, and we can replace this one. This is basically ground, so we don't really need the ground on VO. We can just simply draw it like this, VO. Alright, V out. Next, this pin, the positive, we can see it's got a junction, so we can draw it something like this and make a junction here. One side of the junction got the 150 ohms, so there you go, 150 ohms, and that's connected to ground, and we can draw a ground here. Alright, the other half is connected to 200 ohms, and also 8 volts is coming through it. So we can draw a circle and put 8 volts as the source, 200 ohms going through it, and it's connected here at the junction. Okay, so we already simplified the first half. Now let's simplify the second half. Again, we draw something like this, and we draw here the junction. Okay, because it's a junction in here, even though there's no current coming through these points either, remember the junction always stays there. Okay, when we're drawing. Then we can see that V2, this junction here, is connected to 70. Let me put like V1 for this junction here, and then V2 for this junction here. It's connected to the 75 ohms, and that one is connected to V out. So the way we can draw it is like this. The resistance here of 75 ohms and connected to V out. And this one is got 8 volts going through a 100 ohm resistor and then coming through V2. So again, we can draw one of these circles, 8 volts, and draw a resistor. There you go, connected to point V2. That's got 100 ohms. Alright? Okay. Nice and simple so far. And it gets only easier from this point, because what we have here, it's an inverting with a voltage divider. So this amplifier looks very complicated, but in reality this is, let me grab one of the previous examples that we had. There you go. No, it's oh, there you go. So this looks very complicated in the first step, but once we simplify it to this form, is basically this here from this example. Oops, sorry, from this example. Let me put this on a bit higher so we can compare them. Okay, so basically we got the resistance connected to V1 and to the ground here. We got the resistance V3, and remember again we got the junction here that had 8 volts, so we just split it in two parts. We got the 8 volts going to the 200 ohms coming to V1 like in here, and we got the 2 volts coming to the point V2 with the resistance, and then the V2 coming to V out like this throughout the resistance. So basically what this is this circuit. It's a simple circuit. Okay, so the way we solve it, it's like any other normal circuit. We have to determine the voltage inside V1 by applying the, let's apply the current rule this time. So we have a current going I in this direction, so then I V1, you know, just to mix it up a little bit, it's equal with 8 volts over 350, because I got bored of the let's say that I got bored of the voltage divider rule, so let's do it in other methods. So 8 over 350, that will be equal with 22.85 milliamps. Okay, 22 point, oh, let's put 86 milliamps. All right, so then V1, this one here, will be equal with this resistance, will be equal with 8 volts minus this resistance here multiplied by the current, 200 times 22.86 milliamps. Alright, and that will be equal to, so let's see here, 8 minus 200 times 22.86 times 10 to the minus 3, that's equal to 3.428. Alright, 3.428 volts. Nice. So that's the voltage inside V1. Okay, now what we need to do is, because we know V1, then V2 is equal to 3.428, so then we do 8 volts minus V2 divided by 100, 8 volts minus V2 divided by 100, it's equal with V2 minus VO over 75 ohms. V2 minus VO over 75 ohms. Alright? Okay. Then, therefore, we just need to replace the V2. So 8 minus 3.428 over 100, it's equal with 3.428 minus VO over 75. Alright, then the next step would be to calculate it. So then that's equal with, again we take the calculator, 8 minus 3.428, that's 4.572, let's divide by 100, that's equal with 45.72 milliamps, equal with 3.428 minus VO over 75. So we multiply this number by 75, then therefore that will be 3.429, it's equal with 3.428. Oh my god, this is so small. Isn't it a negative value? No, it's unfortunately positive, and this one is positive as well. Oh no, this is bad. Okay, what I mean by this is bad, I guess I should have increased the resistances. Yeah, I should have totally done that. Alright, let's go back and fix it. Okay, the problem that I have with this is because we move it to the other side, you know, and then VO will be equal with minus 0.001. And if that's the voltage output, then this is not even an amplifier anymore. This is basically just a buffer. The increase or decrease, it's so small. It's not really small. It just, I don't know. Let me check. Like the gain, it's really big, I guess. So it will be like 8 divided by 0.001. Yeah, it will be a gain of 8,000. You don't really want a gain that big, do you? Okay, let's increase the reference then. So let's go back to it, and let's say that we don't want to be 75 in here. Let's say it's 500, okay? So then it will be 500 in here as well. So then that will be 500. Alright, so this will be 500 as well. And now I'll write it with blue. Now when we do this one, because this one's got a gain of, let's write it, gain equal with 8,000, and that's bad. It's too big. It is literally just too big. I mean, theoretically it's not really 8,000, it's like 1 over 8,000. No, not 1 over 8,000. It's a negative gain. So let me check. What if I put like 8 over 8,000? Yeah, I guess I write it like the gain is not 8,000, it's more like 1 over 8,000, because it goes down. Like the voltage output is lower than the voltage input, so it's a down gain, so it'd be 1 over the gain. Anyway, okay, so let's just change it to 500 and calculate that way. So let's say this is 500, so we do 75.42 times 10 to the minus 3, that's 500. And that will be equal with 22.86, okay. So that will be 22.86 equal with 3.428 minus VO. Therefore, okay, so we do minus 3.428 minus VO will be equal with 19.432, and then therefore VO, yeah, it's a minus for the gain. Let's save it like that. VO will be equal with minus 19.432. Alright, and this one is more logical. So the gain, it's equal with 8 divided by, no, it's 19.432 divided by 8, and then that will be equal with, so then 19.432 divided by 8, it's got the gain of 2.429, which this one is good. Okay, again, an amplifier that makes the input 8,000 times smaller is bad. It basically just stops all current and all voltage going through it. But again, that increases by 2.429, it's more logical, so it's good. I don't know, like, I guess you could use an amplifier to stop voltage and current, or to lower the voltage really drastically. But the question is that, what's the point in doing so? You can literally just put a diode and you stop all the voltage going through it, you know. I don't really see how you can actually make this one work. But anyway, I mean, that's why I consider this bad, because 8,000, like a gain that lowers it by 8,000 is bad, in my opinion. but maybe you can find some uses for it. Anyway, so this was this exercise. I mean, I plan to like use this one to show you that you can simplify a circuit, an op amplifier circuit, to something like this by just spreading out the components. But apparently I showed you that this RF is very important, because you can see it's a small difference from 75 to 500. It's not really that much, it's only 425 difference, but it made a huge difference in the gain. Instead of being like the gain being smaller by 8,000, it changed it to a gain that's positive to 2.429. Anyway, thank you for watching this exercise, and I'll see you in the next exercise. Hello again, and this one is another exercise, but this time not only that we have a double amplifier gain, but also we have more junctions to the reference points. Okay, now let's start basically by just notating here. So no current going through here, no current going through here, no current going through here, no current going through here. There are only 2 volts in here, so at this point, at this node here, there will be 2 volts, and very importantly, there are 4 volts here. That means that at this node there will be 4 volts. Okay, now another things that are important is that there's a current I coming through here, but this I spreads into currents. It will spread into I1 up here, and also spreads into I2 down here, so it spreads into currents. So it will make Kirchhoff's law a little bit more difficult, but not impossible. Another thing important of value is that this is 4 volts, but there is no resistance on this wire here, so it's in parallel, so then this will also be with 4 volts. Another thing to know. And also this one will be again split into current, because the current will come through here as well, and it will go up here as I4, and then it will go here as well as I3. That's the way I have noted it. Sorry, I should put like logically I should put like I3 here first and then I4 here, but I'll leave it like this. I can notes I3 here and I4 here, so I don't mix them up. Anyway, so yeah, and what we need to do is to just find the voltage output. Alright, it's simple enough, isn't it? So what we can do, well, we can apply, first of all we apply Kirchhoff's law here. And what do you mean by that? Well, we know this is I, and in Kirchhoff's law this I should be equal with the I on the other side here, but the I on the other side is spread into smaller i's, so you can say that I is equal with I1 plus I2. Alright, now let's go under here and let's replace it. So I will be equal with 0 volts minus 2 volts divided by 4k, 0 minus 2 volts divided by 4k, and that will be equal with 2 volts minus 4 volts divided by 2k. I1 here, because there are 2 volts at this point here, so these points here are 2 volts as well, in case you didn't realize. So this is 2 volts, this is 2 volts as well. It will be 2 volts, this point here is 4 volts, and it's got 2k in here. Now the problem is that there is a VO out here as well, VO out 1 here. We don't know the voltage at this point. Okay, so when we do plus I2, we can see that there are 2 volts coming in, but it's an unknown voltage here, minus VO1 over, and we have the resistance of 3k. Okay, what we can do, well, we can like rewrite it and put and replace the voltages, so that therefore minus 2v over 4k is equal with minus 2 over 2k plus 2v minus VO1 over 3k. Okay, 2 over 4k, that will be equal with minus 5 times 10 to the minus 4, and that's equal with 2 over 2k, that will be minus 1 times 10 to the minus 3, plus 2V minus VO1 over 3K. 2V minus VO1 over 3K. Alright, so then therefore we move it to the other side. This one becomes positive, so it'll be 5 times 10 to the minus 4. Instead of the minus, it's a plus, equal with 2V minus VO1 over 3K. So multiply the 3K by this value here, 5 times 10 to the minus 4. So then that will be 1.5 equal with 2V minus VO1. So therefore 2V minus 1.5, that will be minus 0.5 volts, and that will be equal to minus VO1. So and therefore VO1, surprisingly enough, will be a positive 0.5. Alright, so that was simple. So that's 0.5. Okay, so we have this voltage here. Now we can calculate the rest of it. So let's put a line here, the dotted line, because we have finished the first half here with this this amplifier. Now we know what voltage is coming in to this point here for the current I. Alright, again, this one is coming in here, but it doesn't split, it simply goes along. So this I3, it's equal with this current I1 plus I4. Okay, now I4, no, let's start with I3. I3 will be 4 minus VO over 10K. So that will be 4 minus VO over 10K. That will be equal with I1. I think we already know I1, don't we? Let's see. Yeah, I1, it's the 2 volts minus 4 volts over 2K plus, and now we have it here. We have VO1 minus 4 volts over 5K, and that will give us the I4. So VO1 minus 4 volts over 5K, and because we know VO1, then V out is the only unknown. So then therefore 4 minus VO over 10K is equal with minus 2 over 2K minus 0.5 minus 4, that give us 3.5 volts over 5K. Alright, therefore 4 minus V out over 10K will be equal with 1.7 times 10 to the minus 3 amps. Alright, so then therefore 4 minus VO would be equal with minus 17, because we do 10K multiplied by this value here, and then this is a minus here, and then therefore minus VO will be equal with minus 21, because the positive 4 goes the other side. That will give us minus 21 volts, and therefore V out it's equal with 21 volts, and that's our final answer. Alright, okay, so this is the answer for this problem here. That is spread the currents. Now if I have to say something, is that remember the currents, yeah, remember that these two together, they will give the current I, but also very importantly, remember that this current doesn't really go in this direction like this to the output directly. There is still I1 coming through, so there is still another current coming through here, so you need to count both currents, I1 and I4, to get I3. Okay, so don't forget about this current, and don't think that there is no current going through here. Okay, all right, this was another simple and fast example, and hopefully it's correct, but I don't think it's not correct. I think it is the correct way to calculate, right? And again, if it helps you, do like I do, just put the voltages and the current in multiple places to like figure out how to calculate it, what formula to apply to it, you know. Anyway, thanks for watching this exercise, and I'll see you in the next exercise. Alright, let's go to the next one. And you may already notice that this one is different from the other ones. We have the normal non-inverting, but this also an inverting. Let's say this is the inverting, and we also have an inverting connected together at the V out. And it's a little bit strange because, well, which way do you do it? No, is it either a minus value or is the plus value? And also another strange thing is that we don't really want to know the voltage output here. I want to find out the current here going through RL. If there are only two resistors, then this will be very, very simple. The problem is that there are actually three of them. We have two R2s in here, and we have one RL in here. Okay, so let's get started. First of all, no current going either through here or here, and we got the V prime here, and we got the V prime here. From what I assume is that we are going to really need only the both side here, the downside, but we'll see as we progress. Okay, first of all, let's determine what we need to know to find IL. So IL will simply be equal with 0 volts. No, it will be equal with V prime at this point here, because it will also be equal at this point here to be V prime minus 0 divided by RL. So V prime minus 0 divided by RL, and then therefore V prime will be equal with IL multiplied by RL. So we kind of have a formula for V prime. Okay, next we can determine IL by simply doing these calculations. So this one here is the current coming inside the node, and this will be the current leaving the node. So it kind of like splits up at this point, and this is the original current. So we can say that I, let's call this one IO, I guess. So I would be equal with IL plus IO. Alright, I is 0 minus V prime over R2 equal with that will be V prime minus 0 over RL. No, let's leave it just like IL, because we don't really need it to split it, plus then we get V prime minus V out over R2. So V prime minus V out over R2. Alright, so we'll multiply by R, so multiply by R2. So then therefore minus V prime, we get rid of the R2, will be equal with IL times R2 plus V prime minus V out. Alright, therefore now we just need to rearrange it. V out will be equal with 2 times V prime. The reason is like 2 times V prime or 2V prime is because it's already a V prime, and this minus V prime will be moved on this side and it will become a positive, so it'll be plus V prime plus V prime, so that will give us 2 times V prime, and this one stays the same, plus IL times R2. Alright, therefore V out will be equal with, now we use this formula here that we already made, IL is equal times RL for V prime, so you can say it to be 2 times IL times RL plus IL times RL, no, times R2, sorry. And I think you already know where I'm going with this. Therefore VO will be equal with 2IL times RL plus, no wait, sorry, therefore V out will be equal with IL bracket 2RL plus R2, because this will become 2IL and we can cancel one of them. Let me think. So there are IL on both sides, okay. So we can use only one IL. This cancels, yeah, this is it. It's IL multiplied by 2RL plus R2. Alright, so this was the first half. But again, we still don't know what the value of IL is. I guess we could leave it like this, but we want to have something a bit more precise. So we can, now we're going to use the top side with the voltage source. Okay, so Vs minus, let's draw the current. So this current I coming through here, and this current I coming through here. Okay, so then Vs minus V prime over R1, as seen here, will be equal with V prime minus V out over R1. Alright, they are the same, R1, they are the same value, so then we can just cancel them. Therefore Vs minus V prime is equal with V prime minus V out. Therefore Vs is equal with 2 V prime minus V out. Alright, next step will be to replace these values. So then Vs will be equal with 2 times IL times RL minus, and we know that V out from this formula here, let me like highlight it with blue, is equal with this. So then Vs minus IL times 2RL plus R2 will be equal with 2IL times RL minus 2 times IL times RL minus IL times R2. Okay, oh no, IL, oh this is R2, and yeah, this should be RL, so it should be fine. Then Vs, voltage supply, will be equal with, and if we calculate this, we'll get minus IL times, and RLs cancel each other, so it will be only R2 left. Alright, therefore, now this is the simplest way. IL is equal with minus Vs divided by R2. So there you go, it was a bit lower. So the last result is Vs is equal to minus IL times R2 after calculating this equation here, and then IL will be equal to minus Vs over R2. Now this is the simplest way we can do it, because we can just use the voltage source. We can determine the voltage source and the resistance R2, the value on it, to just have any current we wish to have here. Now the thing is, we could have stuck to this formula here as well. The problem with this is that we will have to take into account more variables. You know, we'll have to find a variable for RL as well. We'll have to find one for R2 as well, and very importantly, we will need to know the voltage output. So this one wasn't really that good. That's why we need to like input here Vs as well, and to replace V out with something that we know, because we know these values here. What we don't know is V out, which was the equal here, you know. And this is possible only because both sides are connected to V out. So this is a little bit strange, but sometimes you want a specific current to go through here, and okay, sorry, my sister walked in. So yeah, sometimes you need to like determine the current to this resistor. I don't think this is good. Like, I don't think you really use this in real applications. I mean, there are better ways to do it. You don't really need an amplifier for it. But maybe, I mean, if the teacher is strict in exams or in tests, I guess he'll do this to you. I guess he'll be like, oh, calculate this current that goes straight to ground as a load, and to check if you know how to do it or not. But maybe you're liking it actually gives you values, like numerical values, because it's always a bit harder to do it like this when all the values are kind of unknown, you know, and to get a formula that sticks with than using numbers. But again, remember, usually it's also better to use something like this when you want to change the variable of the source quite often, and it's just easier to like move it up and down, you know, to like calculate the final answer quickly. Anyway, thanks for watching again, and I'll see you in a bit. Okay, now this will be the last one for this video, and again, it is kind of short. I mean, like, all of them are short if you think about it. I mean, like, it doesn't really take longer than one page, but the tricky part is to like figure out how to solve it. All right, again, our red pen, and let's start doing the basics, the stuff that we know. If we know there's no current through here or here, we also know there's no current through here or here. All right, we know this dot here will be V1 because of the positive. That makes this dot here to be V2. Right, this one will be VO1 because it's the output of the amplifier. Simple so far. Again, we apply the same one. So this one will be, actually let's call this one V1 V1, and this one let's call it V2 V2, because that's basically the same anyway, and it will make it a bit more, it make it complicated if you put like 1 2 3 4 and so on. It will make it confusing, not complicated. Alright, and this dot here will be the voltage output. Now we need to find the voltage output, and we know these answers, not the answers, these specifics. Okay, let's see. Something that you might notice straight away is that it's because there's no current going through here, this one is going straight like that to the voltage output, and we are going to need to remember this because it will become important. Okay, actually start with this one because it's got the same current and it's the easiest one to calculate because it gets us straight to the voltage output. So then V1 will be equal with, so it's a voltage divider. So to find V1 we need to do 2K multiplied by V out divided by 2K plus 14K. Alright, okay, therefore 2K times V out over 16K, and we can do 2K divided by 16 in order to like simplify it and get an easier number to calculate, which would be 0.125 V out. Alright, so V1 is basically equal to 0.125 V out. Now the interesting part is that we can replace it up here as well. And this part here we can say this one will be equal to 0.125 V out instead of V1. Alright, so let's start doing this one here. So this one's the result. So the current, this is I, and the same current will go out this way. Alright, so then 2V minus V1 divided by 2K, it's equal with V1 minus VO1, so V1 minus VO1 over 4K. Okay, very simple and straightforward. Now, therefore, let's see, this one will be 2V, this one will become 0.125 V out over 2K, and that will be equal with 0.125 V out minus VO1 over 4K. We still have two unknowns, but you'll see it still works. So this is 2K, this is 4K, so we can multiply this one by 2, so we can bring both of them at the same number. So then that will be 4V minus 0.25 V out equal with 0.125 V out minus VO1. Therefore, for V minus 0.375 V out, that's equal with minus VO1. Alright, and therefore VO1 will be simply equal with So 4 minus 0.375 VO1, no wait, that's, yeah, let's reverse it and then switch the signs. So we switch to the minus, so that will become a positive. This one will become a positive, so it'll be 0.375 VO, and then this 4 will become a negative because it was a positive, so it'll be minus 4V. Sorry, I need to pause. Sorry about that, my sister and brother were getting loud. Anyway, so let's keep going. So VO1 will be equal with 0.375 VO minus 4V. You may say, well, Alex, yes, but you still don't know what VO is. So how do you solve it from this point on? And yeah, we don't know what VO is yet, but we know we'll get to it eventually. So we can keep it in this form. Also because this was the first amplifier, now we're at the second one. And the second one kind of follows the same formula. So VO1 minus V2 divided by AK. So VO1 minus V2 divided by 8K. It's equal with V2 minus VO over 16K. V2 minus VO over 16K. And likely for us, we already know that V2 is equal to 2 volts from this point. So this one will be 2 volts, okay? Okay, so now what we need to do, we can multiply this side by 2, we get the same number down here. Let me just make sure that you can see all of the calculations. So we get the same number down here, and therefore, and she's shouting again, 2VO1 minus 2V2, that's equal to V2 minus VO, okay? Now we just do some calculation and we simplify this formula to just separate it with the VO, okay? Now, minus VO, that will be equal with, we move the 2VO to the other side. No, 2VO stays the same, to VO1. Then we move V2 to the other side, and that one will become a negative. So it'd be minus 3V2. Alright, therefore, minus VO, that will be equal with 2. Sorry, I need to pause until they get quiet again, because they are playing with those Nerf guns and they will shout at each other and start crying in a minute. Okay, hopefully it's quiet now, but I doubt that. And it's each at the end, so I'll need to calculate only a little bit more. Okay, so that'll be 2VO1, and then we replace the V2 with 2, so I do 3 times 2, that'll be minus 6 volts. Alright, therefore, now we need to replace the VO2, no, VO1, okay? So minus VO, that'll be equal with 2 times bracket 0.375 VO minus 4V minus 6V. Alright, therefore, minus VO, that's equal with 0.75 VO, 2 times 0.375. Wait, is it actually that number? Let me check. 0.375 times 2. Yeah, it is 0.75, okay. So 0.75 minus 2 times 4, that'll be minus 8. And minus, and the 6 that's left, 6. Those are the voltages. Right, therefore, minus VO, that, no wait, let's actually calculate. So then this is a positive, this is negative, we move this on the other side, it become minus 0.75, so we add them together, so we get minus 1.75 VO, which will be equal with minus 14 volts. And let's make both of them positive, so 1.75 VO, that will be equal with 14 volts. Alright, therefore, when we do the division, then VO will be equal with 8 volts. Alright, and if you wish, we can calculate the gain. So after all, the gain will be equal with 8 divided by 2, and that one will be equal with 4. So this entire circuit has a gain of 4. But also remember that this is available if we change this voltage here and this voltage stays the same. If we change this voltage here, then obviously the gain will be different again. Anyway, thanks for watching, and hopefully I'll see you next episode. and hopefully to be a bit more quieter in my house to, yeah, but it's always loud, so I doubt that. Alright, see you in the next episode where we keep doing op amplifiers.